So we're given this linear transformation and we're asked to compute a basis for the kernel of T and the image T. And to compute these two bases, what we're going to do is we're first going to create a matrix representation. In that matrix representation, we can use any set of basis vectors as our input and our output. Because we can use any set, we're going to use the standard basis for alpha, being E1, E2, and E3, and beta is going to be the set E1, E2. Now, remember that this here, E1 is 1, 0, 0, whereas this E1 is 1, 0, because this is the standard basis for R3, and this is the standard basis for R2. Then what we're going to do is we're going to look at what TE1, TE2, and TE3 outputs. And it outputs the this is the same thing as T1, 0, 0, which is equal to 1 minus 1. We also get that T of 0, 1, 0 is equal to minus 1, 1. And T of 0, 0, 1 equals minus 1, 1. Now, we're going to keep track of these later, and we're going to come back to this computation here when we're referring to the image. But for now, let's carry on to figure out our matrix representation, because this equals 1E1 plus negative 1 E2. This equals minus 1 E1 plus 1 E2. And this equals minus 1 E1 plus 1 E2. And this gives us that T alpha beta is equal to the matrix 1 minus 1 minus 1, 1 minus 1. Okay. Now, this matrix is a useful matrix, but in terms of solving for the image in the kernel, the question is why? And what we're going to do is we're going to start by looking at the kernel. And to solve for the kernel, we're going to figure out a linear combination of these output vectors that give us 0, or A T E1 plus B T E2 plus C T E3 equals 0. And we're going to solve the solution to this. We're going to solve for the vector ABC such that this is satisfied. To solve this, we're going to construct a system of equations, and we're going to use that system of equations to figure out our kernel. Well, last time we learned that this linear combination ABC of TE1, 2, 3 is actually T alpha beta, the 0 vector in W. Or in our case, 1 minus 1 minus 1, 1 minus 1, 1, 0, 0. So by creating this matrix representation, we get the augmented matrix of this system of equations for free. We don't need to go through and solve it. We know what it's going to be given our matrix representation of the operator T. From here, what we're going to do is we're going to do row operations to echelon form. So row ops to echelon form, which in this case is simply R2 plus R1 replaces R2, gives us the matrix 1 minus 1 minus 1, 0, 0, 0, 0, 0. And we are in echelon form. At this point, there's a couple things to know. First, our basic variables are A, and our free variables are B and C. Okay. The second thing to note is that I can solve for a solution vector A, B, C. So we can solve for the solutions vector A, B, C. Now this solution vector doesn't give us our kernel, but we can use it for our kernel. And later, when we talk about the image, we're going to talk about our basic and free variables. So now let's solve for our vector A, B, C. Consider a general solution A, B, C. And the system of equations A minus B minus C equals 0, 0 plus 0, 0A plus 0B plus 0C equals 0. Let B equal T, an element of the reals, and C equal S, an element of the reals. Then A equals T plus S, updating A, B, C gives T plus S, T S. This means that T plus S, T of E1, plus T of E2, plus S, T of E3 equals 0. Which implies that T of T plus S E1 plus T E2 plus S E3 equals 0. Which implies that T of T bracket E1 plus E2 plus S of E1 plus E3 equals 0. Now, why have I done this? Why have I expanded in and gotten the vectors here? Well, this here is this here represents all the elements of the kernel of T. Because those are the elements, those are the combinations that will give us 0. Which means I can use this vector here, whatever it is, and this vector here. They are my basis vectors for the kernel of T. And these two vectors are the vector 1, 1, 0 and 1, 0, 1. So the set 1, 1, 0 and 1, 0, 1 is a basis for the kernel T. Two things to note here. First, the number of free variables is the dimension of the kernel of T, or the nullity of T. And second, that's my first. Second, this same process works if we replace E1, E2, E3 with V1, V2, V3. Meaning that instead of using standard basis vectors, I can use any set of basis vectors, solve, plug in here, expand these pieces inside, rearrange, and then compute what V1 plus V2 would be and V1 plus V3 would be. Whatever those outputs of those vectors are, give us the basis for the curve.